Hello, and welcome to Chapter 8, Section 2, Graphing Rational Functions. So when you graph rational functions, those are the functions that look like a fraction. We will use the acronym RADI to help us remember what to do. So I'm going to go through each step while going through another problem. And then I'm going to do two more problems. So R is for roots, or zeros. You factor the numerator and the denominator, set the numerator equal to 0, and solve. You graph these points on the x-axis. So now that we've read step 1, we're going to do step 1. So on the example below on your paper, it says graph f of x using radii. Now R says R is for roots. So we factor the numerator and the denominator. Well, it doesn't need to be factored. So instead, we're just going to set the numerator equal to 0. Well, our numerator is 3. So we set 3 equal to 0. Well, this is a weird case because 3 is not equal to 0, so the answer is none. There's nothing to graph on the x-axis. Let's go back. Now let's go to step 2. A is for asymptotes, vertical only. Now an asymptote is a line that a graph can never ever touch, and I'm going to show you that when I actually draw my graph. We set the numerator equal to 0 and solve. Then we sketch the vertical lines as vertical asymptotes as dotted lines. So let's go ahead and do that. For our A, we take our denominator, which is x minus 5. We set that equal to 0. Now if you were to solve for x, we would add 5 to both sides, right? We've done this before. So x equals 5. That is a vertical asymptote. That means we have a vertical line, a vertical dotted line where x equals 5. So you've got 1, 2, 3, 4, 5. So we have a vertical dotted line right here. That will help us draw our picture. T, number 3. T is for tangency, or togetherness, which we don't deal with in this class, so it's always just none. So when we go over here to do T, it's just none. That's simple. 4. End behavior. E is for end behavior. End behavior is a horizontal asymptote. So we had our vertical dotted line. Now we're going to have a horizontal dotted line. And we have 3 options here, each that has their own acronym, where we look at the highest exponent for x on top and on bottom. There's BOBO, bigger on bottom 0, BOTN, bigger on top none, and SDDC, same degree divide coefficients. This is super important, and you do have to have them memorized because you have to know when to use what. For instance, when we go to our E for 3 over x minus 5, we have 3 over x minus 5. Okay? That means that x on the bottom has this exponent 1, that imaginary exponent that's not written but is actually there. On top, we don't have an x at all. So that's the same thing as saying 3x to the 0 power. Now you have to remember that when we do this, we're looking at these numbers right here. So is 0 bigger than 1? Is 1 bigger than 0? Or are they the same? Well, 1 is bigger than 0, so it is bigger on bottom. That means we are using BOBO. Bigger on bottom, and then it's 0. So our graph will have y equals 0 as a horizontal asymptote. Okay, so if you don't get that, that's okay. And we'll do more examples, but for now, our horizontal asymptote is on the x-axis. 5. 5 is for y-intercepts. For y-intercepts, you let x equal 0 and solve for y. Those are on the y-axis. So, let's go ahead. Plug in 0 for x. We have 3 over 0 minus 5. So we really have negative 3 over 5. That is a point on the y-axis, which is about here. Now when you actually draw your graph, we use our lines to guide us. Our lines can never touch those vertical or horizontal asymptotes, the dotted lines. It can't touch it, but it'll follow it. So we're going to draw this line going around like that. Then, if it's in the bottom left, it has to be in the top right. If it's in the top left, it has to be in the bottom right. So they have to be in opposite corners. If one's over here, the other one has to be over here. So we've got this little curve. It looks like that. Now for domain and range. Domain and range are still left to right and bottom to top. Left to right and bottom to top. So as we go to the left over here, right, we will continue to move, right? We will never stop going this way because that arrow is pointing that way. So we start at negative infinity, but we can only go until we get here, right? It's going down right here at 5. So we go until we get to 5. Then we're picked back up here. So we will union that, which just means it's just another fancy word for and. It's a symbol for and. At 5, and keep going on forever. So our vertical asymptote determines the domain. Our range is very similar, right? We're going down forever. So we start at negative infinity. We go up until we get to this arrow over here, right? That arrow that we already drew. And that's at 0. So we go until we get to 0. We union that with 0 to infinity because we're in the top as well. All right, let's go do another example. So for this one, we have x minus 1 over x plus 2. Well, if you turn over your paper, you know that r is for roots, or zeros. We set the numerator equal to 0, so x minus 1 equals 0. Solve for x. Well, this time there is something, right? We add 1 to both sides, x equals 1. That's a point on the x-axis. For our a, we set our denominator equal to 0, so x plus 2 has to equal 0. Well, if you solve that, we get minus 2 on both sides, and x equals negative 2 is a vertical asymptote. Okay, that's a vertical line. So we have a vertical line wherever x equals negative 2, which is right here. T, there's always none. E, we have to look at those exponents. So we have x minus 1 over x plus 2. What that means is that we've got this imaginary 1 on both of our x's. So is the 1 bigger on top? Is it bigger up here? Is it bigger down here? Or are they the same? Well, in this case, they're the same. So we use SDDC. Same degree, divide coefficients. So we really have the coefficient in front of x is 1, and the coefficient on the bottom is 1. So we have 1 over 1, which is 1. That means we have a horizontal line, dotted line, at 1. So we'll be up here. Y is where we plug in 0 for x, so we get 0 minus 1 over 0 plus 2. So we really have negative 1 over 2, which is just negative 1/2. That gives us a point down here, and we draw our line. So we've got this curve down here following our dotted lines, and if we're in the bottom right, we have to be in the opposite corner, so we're in the top left. Now for domain, we're going left to right. We start at negative infinity. We go until we get to our vertical asymptote, which was at negative 2, union, negative 2 to infinity. So they always end up being the same number. You shouldn't have different numbers for your domain and range, okay, after your u. For the range, we're going from negative infinity up until you get to 1, because that's where your horizontal asymptote is. Union, 1 to infinity, and we're done with the problem. So as you can see, the problems go faster as you know what radii stands for. Let's do one more. We've got r, so we set our numerator equal to 0. That means that 3x minus 4 needs to equal 0. You solve for x. So we add 4 to both sides. 3x equals 4. And now we divide by 3. So x equals 4/3 is a point. Well, 4/3 is a little bit bigger than 1, so it's over here on the x-axis. For a, we set our denominator equal to 0, so 2x plus 6 now needs to equal 0. You subtract 6 from both sides. 2x equals negative 6, divide by 2. And x equals negative 3 is our vertical asymptote. That means we have a vertical dotted line where x equals negative 3. T is always none. And it's in there because in the future you could end up learning about t. E is about your exponents again. We have 3x minus 4 over 2x plus 6. On top there's a secret 1. On bottom there's a secret 1. So is it bigger up here, down here, or is it the same? Is it bigger on top, bottom, or the same? This is same, degree, divide, coefficients. This time we have different numbers though. We actually have this 3 in front and this 2 in front. So when we divide coefficients, we get 3 over 2. And that's what y equals. Well, 3 over 2 is about 1.5, or it is 1.5. So we will have a line at 1.5, which is right here. Now we just need to find our y-intercept. So we plug in 0. We get 3 times 0 minus 4 over 2 times 0 plus 6. Those go away. We end up with negative 4 over 6, which simplifies to negative 2 over 3. Well, negative 2 over 3 is about negative 0.6. So we will plot negative 0.6 on our y-axis. When we draw our line, we follow those points, right? We know which side to go to because it's where the points that we graphed were. Then we know the other side because they have to be in opposite corners of our asymptotes. So there we go. And domain and range are the same as they were the last time, right? You're dealing with your vertical asymptote for your domain and your horizontal asymptote for your range. That's what's helping us. So we go from negative infinity to our vertical asymptote, which was negative 3, union negative 3 to infinity, because these numbers are always the same. Then our range is negative infinity to our horizontal asymptote, which in this case was 3 over 2, union 3 over 2, same number, to infinity, because these are the same. And we're done. We have graphed rational functions. Have a great day.